In this video, we're going to talk about the 1,4-dioxygenated patterns, right? So basically, this is a continuation of our video series, which is the retrosynthesis analysis. Now, let's say you have encountered with a molecule like this. First of all, I have told you when you have a molecule to propose a retrosynthesis pathway, you need to understand the pattern, right? There are specific patterns, so you need to understand the particular pattern for each molecule. So you can see, if I put number 1 for this particular carbon, the next oxygenated carbon is occurred at number 4. So this is 1,4-dioxygenated patterns. Now when we think about a path or disconnection to simplify this molecule, most of you would think a disconnection like this, right? So if you have watched our previous video, right, you will directly go through this disconnection, which this is the most common one, right? This is the most common one. So you know what the synthetic equivalents for this particular synthone? I guess it's a alpha halogenated compound. So this is bromine, and this is just the same. Okay, this is fine, right? This method is fine, but the thing is, there's a much better way to obtain this particular target molecule. So you know, this retrosynthesis pathway is based on the reagents, right? You need to propose a best possible pathway. This is fine, this is correct, no one can tell that this is wrong, but if your particular molecule has a better pathway than this, then you cannot propose this pathway. Why? Because you have a better pathway, right? What about this? So let's take a blue color. Okay, now I am going to disconnect this through this bond. Now what I have is this one, okay, and this one. This one and this one. Okay, we have a negative charge here. I hope you know what the synthetic equivalents for this particular molecule, right? This is a very famous molecule, so you can propose this one. This is the synthetic equivalence for this particular molecule. But the thing is, what is the synthetic equivalence for this particular synthone? We have discussed about this in our very first few videos. If you remember, right, now you know retrosynthesis is based on we are going in opposite direction, right? We are going on opposite direction. So the final molecule, the final obtained molecule you get, right, you should be able to synthesize step in the forward direction. So if I draw this molecule, what would you think? I hope now you get it, right? This is a alkyne, right? This is alkyne. So you know this alkyne can directly convert into this particular carbonyl compound, right? It's basically a one-step reaction. So this is our synthetic equivalence for this particular synthone. I hope it's fine, right? I hope it's fine. Now let's look at the synthesis. Okay. Now when it comes to synthesis, you know, this guy can be directly converted into this guy, to Ag2+, right? And I guess it's sulfuric, right? If I'm wrong, please mention in the comment section. I don't remember this exactly, but I hope it's sulfuric. So now we have obtained this. Now what you have to do is introduce the nucleophile. Here we have the nucleophile. Now what happens? This electron can go and push towards here. We can obtain 1, 2, 3, 4, 1,4 dioxygenated compound pattern. So this is the synthesis of this particular molecule. So again, I'm going to tell you, this is fine, right? This is fine, but this is the much better pathway, because this is a alpha halogenated compounds. This usually we cannot accurately say this works. When it comes to practical scenarios, there are some occasions, there are some situations where this pathway doesn't work. So, but this particular pathway, we know exactly, we know 100% accurately this works. So this is a better pathway than this. Again, I want to tell you, like, this is a very special case, right? This is very special case. So you just need to this really, like, this pathway, I mean, this pathway really strict to this molecule. You know, like, if you have a few molecules like this, it may be changed, right? In that case, this is the best pathway. So the pathway depends on your initial target molecule. But if you have this initial target molecule, right, this is your initial target molecule, then this is the best pathway. Normally, like, you won't get a very complicated molecules for your exams when it comes to retrosynthesis. This is a very famous molecule when it comes to retrosynthesis. So please be aware of it. Please get note of put some notes about this particular position. Okay, now let's look at another example. So this video is going to be a little bit longer because, like, I'm going to talk about this particular example a little bit, right? Because this is very important. This is a very famous question for many papers. Let's look at this guy. Okay, so I would say, like, the question is about you need to propose a retrosynthesis pathway for this particular molecule. I would say one of the final reagents is this one. Okay, so you need to identify the other one, and also you need to introduce the synthesis also. Now I hope you can pause the video and try it yourself, and then I will do it. So here, this is the retrosynthesis path. The disconnection path is pretty much easy, I guess. You know, this is 1,4-dioxygenated compound. So this is not this exact molecule, right? So you don't have to go through here, right? It's going to be complicated if you go through here. So the best possible pathway is this one. So you can see, you can disconnect it through here. Let me take some space from here. Now you have two molecules, this one and this one. So you need to just give negative charge for here and positive charge here. So you know this one, this is the synthone, and this is the synthetic equivalence. So this is the synthetic equivalence for this particular molecules. Always remember, right, when you draw the when you write the answer, the arrows should be very careful. The arrow should be very clear, right? If you draw this one-sided arrow, it's wrong. When it comes to disconnection, this double arrow should be there. Now this is my pathway, right? The tricky part is the mechanism. When it comes to mechanism, there's a small catch. If you draw your mechanism like this, okay, if you draw your mechanism like this, in basic medium, right? Let's say in basic medium, this is pretty much so if you're going to draw the structure like this. So this is wrong actually. This synthesis is wrong because this reaction won't occur like this. If you do this reaction practically, okay, if we do this reaction practically, what the product would be like this. You will have a product like this. So this is the product you have. Okay, this is the product you have. So it's not the same product. Now what you can do is, so first I will tell you like why this happens, right? This happens because of the this reactivity order, right? the reactivity. Like we need this particular position, to attack this guy, right? We need this particular position to attack this guy. So we need to highlight this one. We need to increase the nucleophilicity of this particular position, right? And protect this carbonyl group. So in this case, you can see the carbonyl group has been reacted with it, right? The carbonyl group position is the one who has reacted. Now in this case, we need to protect this carbonyl group. So what we can do is introduce a protecting agent. Okay. Now instead of directly putting these two guys together, what we can do is a thing like this. Here we have our compound. First, I'm going to introduce a protecting agent. This one. Okay, so what will happen here? We will obtain this product with the reaction. Okay. This is the product we have from this reaction, and then with the equilibrium we can obtain this one. I hope you can understand this, right? We have a negative charge here and we have positive charge in the nitrogen atom. So I won't discuss about the reaction mechanism here, right? I won't discuss about the reaction mechanism here. It's a simple one, but like due to the time I won't discuss it here. Now in this case, what happens is, this lone pair will go into here to form the double bond, and this will go into here. Now we have this particular structure. Now you can see this position here, right? This position here has a higher electronegativity, right? Compared to this. If you compare this structure and this structure, you will see that this has a high electronegativity, right? Because this is the structure we have. These are the two resonance structures. So 50% of our system contains this negative charge on this position. But if we take this particular compound, 100% of the compound is neutral here. 100% of the compound is neutral here. But in this case, you have a 50% nucleophilicity on this position already. So that's why we are using this type of protection groups to enhance the nucleophilicity of this particular position. So this position can go and attack to our particular compound, and it will protect our original carbonyl group. Now what happens is, we have this compound Br and CO2 Me. Now this can go and attack to this particular position, and bromine can leave on its own. Okay, we have our product like this. Okay, now what we have to do is, we need to remove this protective group from our original molecule. So to do that, simply you just have to add acid in, like, say, methanol, right? Methanol as a medium. So you will obtain the initial target molecule. So this is basically the structure, like this is basically the procedure for your reaction. Like, what you need to understand is, you cannot directly add these two guys together. It won't react. So you need to go through an enhancement like this. So this is very important. This is a very famous question. The question can be asked like based on, like, there can be deviations, there can be some functional groups added to these particular structures. Likewise, the question can be like that. But this is a very famous question and very important point in your retrosynthesis analysis. And Now I will discuss about the mechanism, like what's happening here. Like if you're not interested about this particular reaction, then you can leave the video, like otherwise you will waste your time. So let's talk about the reaction mechanism of this guy here. What would happen with, let's take this one. This is our alpha halogenated compound. Okay. Okay, so this molecule, here I have drawn this molecule. Now what happens is, in basic medium, right, in basic medium, let's say we have Ermi. Now this can go and attack to our acid, and this will form a double bond between our carbons, and this will go here. So we have a product like this. Okay, now if you have your carbonyl compound, initial like cyclic carbonyl compound here, right? Now what we need, right, actually what we want is to attack this position, attack this nucleophile to here, right? This is what we want, right? But in this case, if you use these two reagents together without any interference, without any enhancing agent, right, what happens is, this guy over here, okay, this guy over here, this will go and attack to this other carbonyl position. You know, this is also a carbonyl position, right? So this carbon has a positive charge, like not a positive charge, it has this electrophilic character. So this will form here. So we will have a product like this. Here we have the oxygen. This oxygen is here, right? Here we have the carbon, and here we have the bromine. This is the structure we have. Okay, and now what happens, right? Now what happens? This oxygen here, right? This oxygen here, it can donate its electron density to this carbon, because this carbon is attached to a loosely bounded leaving group. So due to this attack, this leaving group can leave on its own. So we have our final structure like this. This is an epoxide, if you remember. This is an epoxide which is not the product we need, right? We need this product, right? Sorry, we need this one, but it's not what we get through this. So like, if you have a question like this, if you have a structure like this, okay, if you have a structure like this along with another carbonyl group like this, so be very careful about it, right? Because what we want is to attack this nucleophilic position to here, but the other way around is also possible. So in order to facilitate what you want, you need to add a particular reagent or particular molecules to enhance that property. So I hope it's okay for you. Like practice this mechanism several times and do some questions about it, so it will be fine for you. Like again, I would tell you, like, you won't have any advanced questions, or you won't have any like advanced structures for your exams. Like it would be basic. Like I think mostly it would be related to your notes and what you have done in your semester and studies. So only thing the question papers does is, like, it will deviate the structure, like it will add some functional groups and here and there, but the base is the same. You need to understand the structure, you need to understand the pattern, right? Just understand the pattern, then you will be okay. So that's the case in these questions. So I hope it's fine. If you have any questions, feel free to ask.